Hello everyone, my name is Vít Ružička and I'm presenting our work, Unsupervised Change Detection of Extreme Events using Machine Learning on Board. The problem that we are aiming to tackle is that in the current state of remote sensing, when looking at images captured on board of the satellite, they are all considered sort of equal. There is no decision-making mechanism there which would be able to select what is important and what is not. And in cases where there is limited bandwidth, this might lead to loss of some important information or additional costs because we have to pay for the bandwidth in some cases. So the task would be to kind of detect these anomalies on board and maybe using this information, decide what to send down and what not. The goal is to have unsupervised change detection of extreme events on board of this satellite. A baseline approach to this task would be to detect changes in the image space. So when looking at a image captured from previous pass and then current image, look at the same location of the tiles and then compare this in the pixel space. However, this approach tends to be quite sensitive to noise, and so we are trying to work with something else. Instead of doing this, we would be training the autoencoder model on an unsupervised auxiliary task to reconstruct these images. And by doing so, we are also learning to encode these images into some meaningful bottleneck representations. Later, we could use these latent space representations to make comparisons in the latent space rather than in the image space, and these tends to be more robust to noise. Naturally, we can also consider longer temporal series of images, so not only looking at one previous image, but looking at a series of, for example, 3 or more. So the system that we are proposing is called RaVAEn, and it would be a system which would allow for intelligent decision-making directly on board. This means that when looking at new image, being able to answer the question of if this image has changed significantly, and if yes, then we can prioritize the downlink of this information to the ground. And if not, maybe we would still downlink it, but only if there is enough bandwidth available. We can also update the stored representations of this data on board of the satellite using only the latent representation, and these latents are roughly 80 times smaller than the dimensionality of the original images. In order to measure the success of our approach, we have made a dataset of extreme events. We have a diverse unlabeled training dataset over 233 scenes, each with 5 time steps, and a non-overlapping labeled evaluation dataset, again of 5 time steps across 4 different classes. So these classes include disasters of hurricanes, landslides, fires, and floods. And while there has been some work in tackling actually floods as a scenario, we are trying to, within our current work, we are trying to aim at kind of all types of changes, so have a general approach and not to focus on only one. This is the reason why we are trying to do it in an unsupervised manner. This is a prediction example of our model, which our model's prediction is in the lower right bottom corner, and it is relatively cleaner than the baseline approach, which tends to be more noisy and more less robust to this noise in the pixel space. Looking at the numbers, we are comparing our approach on the area under the precision recall curve on these 4 different subsets of the dataset. And to summarize, our proposed method outperforms the baseline solution in most cases when using the memory size 1, and when actually considering all memory of 3, we are outperforming in every scenario. Furthermore, we were able to test this on dedicated hardware, so on the Xilinx Ping board, which is used in real-world satellite systems, and we are showing the results of the best performing method from the previous slide. So while keeping the same, maintaining the model's performance with approximately ±3%, we showed that we can actually reduce the size of the model architecture to have greatly reduced runtime, so going from 14 seconds to 2 seconds. In conclusion, we are presenting RaVAEn, our variational auto-encoder approach for unsupervised change detection. We are releasing both our code and both the dataset, and we have been able to measure this on real-world hardware. Thank you for your attention, and if there are any questions, please feel free to ask.